Thank you. So I should just repeat part of yesterday's talk to orient everyone. I have the same set of slides and I added one. Real quick. So we want to describe zeta values. X is always the same. It has these assumptions, a regular proper scheme of dimension D. So the basic idea is to describe the zeta function at s equal n. We have to look at the weight n motivic complex. That was the actually one of the origins of the ideas of motivic cohomology, coming from zeta values. And everything's very nice and explicit and understood over finite fields. So we have to make this Weil et al. Modification of the Galois of the et al. Hypercohomology of motivic complexes. And if we assume finite generation in a certain range, this Weil et al. Cohomology is a perfect complex of abelian groups. And then we describe the zeta value following this pattern here. So tensor at R, we get a trivialization, and that means that the integral determinant of the motivic complex gives you a number, which is the leading coefficient of the zeta function, up to this additive correction term. So this formula was found experimentally by Milne in the 1980s already, but he didn't have an explanation of this particular number as an Euler characteristic. And so what I wanted to do is really give a one-line proof of this formula here, using what's been introduced at this conference so far. So again, the reason we can prove something is, of course, because we understand the whole function. The zeta function is a rational function, so you can view it as an L-adic valued function for any prime number L. And if we take L equal to P, we have the expression in terms of crystalline cohomology, which is a Weil cohomology theory, so it has the same ranks as the L-adic cohomology, and the same zeta function can be gotten from this. So why can you prove anything? So let's just make a connection to the rest of the conference. So crystalline cohomology is prismatic cohomology in this case, over this base prism ZP, which is a crystalline prism with a perfect prism with trivial Frobenius. So it agrees with this one twist. So in general, you would have to put the one twist. And 1 minus Frobenius on this crystalline cohomology, you can factor into two steps. So first you go by the Can map to the nth Nygaard filtered piece, and then on the nth Nygaard filtered piece you have a divided Frobenius phi over p to the n. And this is exactly what we need to look at for evaluating zeta function at s equal n. So that means now integrally this value has two pieces coming from the mapping fiber of this map and the mapping fiber of this map. And these have well understood meanings. So the mapping fiber of the first map is just Tc, rather the nth motivic graded piece of Tc. And it is known in this situation for something smooth over a finite field that the nth graded piece of Tc, which is symptomic cohomology as defined by Bud Morrow-Scholze, is really the cycle theoretic cohomology, which is at least mod p to the n, just given by this logarithmic de Rham-Witt form. So that's known for the Bloch cycle complex, and it also agrees with this more recent symptomic cohomology defined by Bud Morrow-Scholze. And of course, if we assume this is finitely generated, we just tensor with Zp to get the p-adic completion. And then the other piece is just what I will be calling Tc plus. So this will occur later on again. So it's just the homotopy co-invariance of the S1 action on THH. And of course, this is also given by this fiber sequence. So this is Tc minus, this is Tp. So the fiber is Tc plus up to some shift. And one can compute the multiplicative Euler characteristic is just this Milne's correction factor. So this is, you can first compare it to Hc, and then you have a filtration by the exterior powers of de Rham, and you get this this number here, which was introduced here. So it's really at least if the zeta function doesn't have a pole. So if this vanishes at n, then we have to be a bit more careful. But so this would be the complete proof if there is no pole or zero of the zeta function. It's just this one-line argument why the value has this shape, because you have these two pieces coming in, these two mapping fibers. Okay, so so let me just summarize then what happens in characteristic 0, what I said yesterday. So we again have to look at higher Chow groups as the basic definition of motivic homology in the étale topology. The other key ingredient comes from the Archimedean places, which is Deligne homology, which is some kind of completed motivic homology in a very vague sense, but you can just define it by this Deligne complex. Again, this part here would be giving you the weight n graded piece on cyclic homology. So some kind of tangent space, if you like. And then we defined Weyer-Hakelov groups, which are now quite different from Weyer-Étale groups, but they should generalize the Weyer-Étale groups over finite fields. So again, we have to make some assumptions that are very hard and only known in a few cases. This finite generation assumption, the balancing conjectures, and some Artin-Verdier duality, which fortunately is known in many more cases. So these are the two hard conjectures going into this picture. And once we assume those, we make various mapping fiber constructions and produce a diagram. So unlike in characteristic P, it's not a single group that plays a role attached to X. We have this whole diagram attached to X involving some compactification and some fiber at infinity and some motivic homology over the Archimedean local fields. It's also not true that the complexes are perfect. They live in the derived category of locally compact abelian groups. And so I then introduced the same diagram with Rn and R mod Z coefficients. So for all the terms in this diagram, you have this exact triangle relating Zn and Rn coefficients. You have some expected dualities, and what's relevant for the zeta function is the compact support cohomology. So this is the key triangle which I will be talking about for all of this talk. So you have Zn cohomology, Rn, and R mod Z n cohomology at any integer n. And the basic picture is that for the Rn cohomology, you again have this trivialization, this exact sequence. And the R mod Zn cohomology happens to be compact. So in all degrees, for all twists n, these happen to be compact groups. So they're a torus cross a finite group. So, for example, if this is perfect, then this triangle is just what you would expect. So you have a perfect complex of abelian groups. This is the group, the complex tensored with R, and this is the cofiber, which is then automatically compact. But it doesn't always look that simple, as we saw in the example of the class number formula. Actually, it's here. So these groups are always compact, but it's not true that these groups are finitely generated. Just in degree 3 they are. And then you have this picture Z goes to R mod Z. So what I need to focus on now is what generalizes this measure. So we have compact groups. How do we put a measure on these groups? So here it comes from the natural additive lattice in the tangent space. And we want to do something similar for higher Tate twists. So where does the measure come from? So again, the relation to zeta is given by the same steps as over finite fields. So the vanishing order is the secondary Euler characteristic, and the leading coefficient now is the volume of these compact groups. But I have to put a volume form on them. So I'm not done yet with this statement. So how does that work? So let's first talk about some very simple generalities. So if you have any locally compact group, you define its tangent space to be this, just continuous homomorphisms of R into G. And if G happens to be a Lie group, this is really the tangent space, because there is some theorem telling you that any continuous homomorphism is analytic And once you have an analytic homomorphism, it's in bijection to the tangent space, just by looking at the tangent map of your homomorphism. But you can make that definition for any locally compact abelian group. In fact, for any condensed group, you could make this definition. And you can even put R hom here for condensed groups. There's no higher X in this context. And you have an obvious exponential map by evaluating f at 1. And so in the standard examples, you would have a discrete group has no tangent space. I mean, this is clearly 0. But if you have something like R or R mod Z, you get R as a tangent space. And so looking at the exponential map, you take its mapping fiber, which is now, if G is compact, it's just a lattice. Remember, it could still be compact, a torus cross a finite group. So the co-kernel of this exponential map is then the finite component group, and the kernel would be a lattice in the tangent space. So in any case, L is a perfect complex of abelian groups. And the volume of G you can express in terms of this determinant formalism, right? So a volume form, a Haar measure, is given by a section of the tangent space, a non-vanishing section. And once you choose this volume form, the volume would just be the scalar that matches the given section to the determinant lattice of the tangent of this lattice in the tangent space. So again, this is by functoriality of this determinant formalism. The determinant of L sits inside the determinant of the tangent space, and in there it's a lattice which is just a Z lattice of rank 1. And so there is a factor relating this Z lattice to the volume form, and this is the volume of G. So that kind of links up this determinant formalism I talked about in the first 2 lectures, determinants of perfect complexes, with its volume business. I mean, you can use one or the other to describe L values, if you like. Okay, so now, how do we get a volume form in our case? So first of all, this tangent complex functor extends to complexes. So as I said, you could just take R hom here, and then you can put a complex here into your argument. And so you get a tangent complex functor from our derived category of locally compact abelian groups to the derived category of real vector spaces. And now the complex that we're interested in was this one. So remember, this had compact cohomology groups, and you apply the tangent functor to it. And so this would be a complex of real vector spaces, and this is our original complex. And then the mapping fiber is a perfect complex. Just as in the previous discussion, this L now becomes, on the level of complex, it's again perfect. And we call it Vegetal cohomology, but this is just, I mean, it's not a cohomology theory in its own right. It's just because it's a perfect complex for any n, we call it Vegetal. So it's just, I have to call it something. But it really should be thought of as the lattice measuring the volume of these compact groups here. So I'm still not done. So where do I get my volume form from? So I have to find another section in this tangent space, in the determinant of this tangent space, which is now a whole complex. So it's the alternating determinants of the spaces. And this is the same as the determinant of this perfect complex tensored with R. This is just what I said here. The L tensor R is just the tangent space again. So I somehow have to find another section in this determinant here. So I have one sublattice given by the integral cohomology of this, but I have to find another section that normalizes my volume. And once I do that, then the volume is again the factor matching these 2 determinants. So the mu is really what would be my right-hand side here in the zeta value conjecture. It's this factor mu that relates the volume form to the determinant of the integral lattice. So I still don't know where the volume form should come from. So this is now the key step. So where does this form V come from? So what we do is we look at our triangle number 13, which was back here. Oh, I have a wrong numbering. So it's this triangle. It's actually number 1. So this is the key triangle that's behind zeta values. So you have the Z and the R mod Z cohomology. Now you apply the tangent space functor to this whole triangle, right? So imagine doing that. It's just an R hom from R into this triangle. Now that's already a complex of R vector spaces. So the R hom of R into this doesn't change anything. Here we get the tangent spaces of these compact groups. And here we get something. We get the tangent space of motivic cohomology, which you can compute. So this is what I just said. We apply the tangent space functor to this whole triangle. In the middle, we don't change anything because these are already R vector spaces. This is our tangent space tensored with R, which we can also write like this, involving this perfect complex. And then here we have to compute the tangent space of motivic cohomology somehow. And let's do that in a minute. Let's just take determinants of this triangle. So that means on the level of determinants, we get an isomorphism of the determinant of this with the determinant of this times the inverse of the determinant of this. That's what I'm writing down here. And now we can get rid of this term because the determinant of this was canonically trivialized. That's what I was telling you before by this sequence here. The determinant of the real cohomology is canonically trivialized. So that means we can just ignore this. We can omit this factor. It's canonically R. It's trivialized. So we get an isomorphism between this determinant and this determinant. I have a shift here. Yeah, I mean, if I trivialize R or R inverse, it doesn't matter. So now I still have to compute my tangent space of motivic cohomology. Okay, so this is just what I said in words. So how do we compute the tangent space of compact support motivic cohomology? Well, we look at another defining triangle of it. Remember, in this diagram I had at the very beginning, I can relate compact support cohomology with usual cohomology and the cohomology of the fibers over the local fields. And now this, we had at the very beginning of today's lecture, had this truncated de Rham cohomology in its tangent space. So one piece of this was just the truncated de Rham complex. And if you look at determinants, that's all that remains on the level of determinants. The other part is kind of so why is the tangent? Oh yeah, because I take Zn cohomology, right? So the Betty part in my Deligne cohomology, let's bring it up. So Deligne cohomology had these two pieces here. It had a Betty part and then this. But if I take cohomology of this, I get Betty cohomology with Z coefficients. Now I apply the tangent space functor. There's nothing contributing from this part because it's finitely generated. They're discrete groups that don't have a tangent space. So tangent space only comes from this part, which is truncated de Rham. It should be moving forward. Here we go. So applying the tangent space to this Deligne cohomology, I'm just ending up with truncated de Rham, which is some real vector space. And this has a natural rational structure because analytic de Rham coincides with algebraic de Rham, and everything was base extended from an arithmetic scheme, in particular from X tensor Q. So this has a natural rational structure given by truncated algebraic de Rham cohomology, and rationally that's the correct volume form rationally. So I still have to find the correct volume form integrally. So it's some other section of this rational vector space, a truncated algebraic de Rham cohomology. And And so if you're optimistic, you could say, well, the integral volume form just comes from another perfect complex. Yeah, so we want a natural Z structure on this truncated algebraic de Rham cohomology. Of course, there's no a priori reason why it should come from that. It could just be a numerical factor, right? It's just a volume form, so we might have to put a factor of 2 in it or a factor of whatever. There's no a priori reason why it should also be a determinant of a natural complex that gives us this volume form. But let's just try to find a natural complex whose determinant then is the section giving you the volume form. So, of course, the naive guess, you just take algebraic de Rham cohomology over Z in the naive sense in this rational space. So that's clearly wrong if you look at the examples. And then what we've been working with for a long time is just the derived de Rham cohomology, which has also appeared in this lecture already. And I'll illustrate in an example in a minute why this is much better than the naive de Rham cohomology. And so we were making our special value conjecture for a long time with this derived de Rham cohomology. In particular, over finite fields, it exactly gives this correction factor I was talking about at the beginning. So I told you it's the motivic graded piece of TC plus, but instead it's also the motivic graded piece on HC over a finite field. So if X lives over Fp. So this also gives exactly Milne's factor. And so that gave us some confidence that it's the right thing, maybe in general. But it's not always the right thing, so there's a correction factor. So our volume form would be the determinant of this times some correction factor. And of course, if you formulate it like this, it's completely vacuous, right? Once you put a rational correction factor, you haven't achieved anything. You just know the right rational space, which we knew anyway. So stating things like this is vacuous, but I will try to pin down this correction factor on the next slide. And so then Baptiste realized at some point that there is actually a complex which gives you everything on the nose without a correction factor, which is again the motivic weight n-graded piece of TC plus. Just like on my slide over finite fields I had at the beginning, it's again this theory that seems to be giving the exact volume form on the nose. So it's just this, which I call truncated de Rham of X over the sphere, but that's just the name. What it is, it's really the motivic weight n-graded piece on TC plus. And so that's the conjecture we have confidence in. So again, it says that this volume form, when you measure what it does, I mean, when you compute the volume of these compact support groups, that means you have to find the factor that relates this volume form to the determinant of this Vegetal, and that should just be exactly the zeta value. But let's like kind of step back a little bit and work with this picture that we did for a long time. So what can you say? How can you pin down this correction factor if you don't know? Yeah, I mean, what would be a way? And of course, one way to pin down this correction factor is, well, we certainly want everything to be compatible with the Tamagawa number conjecture of motivic L functions, right? This was the story I talked about in the first two lectures. There was an exact integral conjecture. It looked rather different, but the pictures have to be compatible. So we just defined this correction factor for a long time, just such that the whole thing is compatible with the Tamagawa number conjecture. So, yeah. Yeah. Yeah, we knew it. Oh yeah, the question was, we know what this factor is if we believe in this picture here. So we believe that TC plus is the right theory. We can compute the difference between these two things. It's a bunch of factorials, which I will come to in a minute. And that means if the prime P is large enough, the factor disappears, right? And we knew that. So we could prove that the factor disappears if X is actually smooth over ZP and P is bigger than N. Something, yeah. So you can make a non-vacuous statement by simply putting in the right factor so that everything is compatible with the Tamagawa number conjecture. And so that's what we did for a long time. So that's what I'm saying here on this slide. And then if you do that for trivial reasons, for negative n, there is no correction factor. If you take n equal 1, which is sort of the Z1 case corresponding to GM, the multiplicative group, in particular BSD and all the things people look at classically, it's actually a highly non-trivial computation that the factor is also not there. It's equal to 1. If you're over a finite field, there's also no correction factor because of what I just said before. I was telling you that the weight n-graded piece of TC plus and of HC, which is this, they have the same multiplicative Euler characteristic. They both have finite cohomology groups. They're not isomorphic, but they have the same Euler characteristic. And then the only other case where we could compute this correction factor using this compatibility with the Flach conjecture is this very basic case where you have an abelian extension of Q. And so we could compute it in that case using classical techniques in Iwasawa theory, like the Coates-Wiles homomorphism and so on. And it came out as this factorial. And of course, we would assume that this is the right factor for all number fields, but we could only rigorously prove it for the absolutely abelian case. So in other words, if we put in this factor into our conjecture, everything is compatible with the Tamagawa number conjecture. And so in general, it looks then, I mean, Baptiste guessed it at some point. I was having no confidence that we could anything more about this factor. It's just a factor that we have to leave in, which might depend on bad primes and all these kind of things that, if you're familiar with special value conjectures, which might go wrong. And then Baptiste had the confidence to actually try to find a formula for this factor, and this was sort of an obvious guess. In general, you have to plug in some factorials depending on the Hodge numbers. Here we're in the zero-dimensional case. The only Hodge number is H0, which is the degree. So he was working with this guess, and he even came up with a modification of derived Durham, putting in some factorials in here, which produce this factor before we discovered TC plus. And but once you define things as the weight n graded piece on TC plus, you simply verify, well, it's not simple, it's a paper of Baptiste, you verify that the difference between these two is actually this factorial term, this C infinity as we call it. So the difference between derived Durham modulo field n and motivic weight n graded piece on TC plus is this. And in particular, if X is over a finite field, the generic fiber is empty, and this factor is 1, and we get no difference. That's what I say here. Okay. So now, if you like, you can actually forget about Weyer-Hakeloff groups and all this stuff that I was telling so far. If you like the Fontaine-Perrin-Riou point of view, you can simply talk about a fundamental line again. So remember, what we were saying here is that the zeta value relates these two lattices in the same R vector space. So you just bring this on the other side, and you call this the fundamental line, and you can make a zeta value conjecture using this fundamental line. And again, it would say that tensor R, it's kind of trivialized, which is what I was basically explaining before, and that the zeta value spans the canonical integral sublattice in here, which is this statement. Yeah, the way thing, yeah. So it was the lattice in the tangent space of compact support, and yeah. So now you can forget about all Weyer-Hakeloff groups. You can, if you like the fundamental line so much, you can just talk about this construction and just do as we did in the previous two talks, in the first two talks. It is true if X is smooth proper, so there's no interesting bad fibers coming in. It is true that this fundamental line is just the Fontaine-Perrin-Riou fundamental line of the total motive of the generic fiber. Yeah, so XQ is now a smooth proper scheme over Q of dimension d minus 1. And we just put all the HIs together with a certain T-twist, and we look at the Fontaine-Perriot fundamental line, and that's this thing, tensor Q. In general, you have some stuff coming from the bad fibers, but in this case, also the zeta function just coincides with the alternating product of the motivic L functions, and we show that the conjectures are really equivalent in this smooth proper case. But it's not a priori, there's no a priori reason why there should be such an integral fundamental line, right? I mean, there might be some factors to get the correct L value that you just have to put in by hand. But it seems there is some, it's just this determinant line that gives the value exactly. Okay, so now I want to say a little, well actually I don't want to say it, but I should say a little bit about how we construct these complexes, right? So I was telling you we have to assume severe conjectures like finite generation, and then we do some mapping fiber constructions to get these Weyer-Hakelov complexes. In particular, this one. So how do we get this Weyer-Tal complex? I mean, it's really a silly construction. I mean, it uses Artin-Verdier duality. So this is at least in many cases known. So we have this torsion duality, which simply means that the cohomology in higher degrees, bigger than 2n plus 1, so remember, smaller than 2n plus 1, we expect it to be finitely generated. In higher degrees, it will be co-finitely generated. So you can express this cohomology group as a Q mod Z dual of a finitely generated group in the dual twist and dual degree. So this is kind of rigorous by using Artin-Verdier duality. And then you can make a mapping fiber, so this Hom of this into Q maps into Hom of this into Q mod Z, which in turn maps by duality into this cohomology group, and you take a mapping fiber, so you turn the Q mod Z into a Z in the previous degree just by the fiber sequence Z goes to Q mod Z. And so this complex, this mapping cone will then be perfect. I mean, it's really a silly construction which you could make over finite fields as well. So instead of this Weyer-Tal topology, you could just make this mapping fiber construction to get a perfect complex. So that is Weyer-Tal cohomology over X bar, and then compact support would be a mapping fiber to a certain Archimedean term. So this is a certain lattice in the Betti plus space that we define carefully. So already in the original paper, Baptiste came up with the right two torsion. So everything works perfectly well, including two torsion, and that's the subtlety in the definition of this complex. So these are the perfect complexes that we get for any n. And now the Weyer-Hakelov, you do further mapping fibers, you bring in the real vector spaces and then the eventual locally compact abelian groups to get this picture I mentioned at the beginning. But this is also so weird and non-canonical that I'm not going to go into any details. It's certainly not the right construction. I mean, there should be much better definition of these Weyer-Hakelov groups. Yeah. Yeah. Well, I take the mapping fiber of a Q to Q mod Z, that's Z. So remember, this is a finitely generated group. So the Hom of this into Q is just a bunch of Qs again. Oh. Yeah, because of our key assumption here, right? I apply this assumption to the dual degree and dual twist. Yeah. So this is true for any n. Yeah. So I apply it to the dual, and yeah, it works for negative n. For negative n, what does it say? Well, for negative n, if E is supposed to be less than 2n plus 1, that means I is negative. There's no cohomology. So it just means it's an empty condition for negative n, but it's still true. 2n plus 2. No, this is where you get starting Q mod Z's. Yeah. So this is all experimental. I mean, this is experimental mathematics. I mean, I'm not saying that this should be a good definition. It's a horrible definition, but um, it, it would be very nice to find another definition of these Weyer-Akelov groups. Okay. Yeah, so this is just repeating what I already said. Everything is compatible with the Tamagawa number conjecture if we put in this factor Cxn. And so the question is it really equal to these factorials? So remember, the only case where we could prove the Cxn to be equal to factorials is this case here. Now, how about in general? So this is still not known. So we expect it to be equal, so we expect this quotient to be 1, but it's only known if n is less than or equal to 1 or in this very special case. And to prove this, it's actually related to what Achim said in his previous talk. I mean, you have to relate Tc plus and Tc on the level of determinants. So I could maybe formulate a precise conjecture, but the equality of these two terms has to do with Tc plus and Tc. But let's just say our factor is the right one, so this quotient is 1. Then that means our zeta value conjecture is equivalent to the Tamagawa number conjecture. And so any case you've proven for the Tamagawa number conjecture gives evidence for our conjecture. And again, we only know a very basic case, Spec F, for f is abelian. I told you before, everything's completely proven in this case, so that corresponds to Dirichlet functions. And so that means that our conjecture is completely proven in that case for any n, not only 0 and 1, which is the class number formula. So that's our main evidence for this, that everything works nicely. There is no open conjecture in this special case. Okay, so what else did I want? Yeah, so I want to go in detail to the example Spec F, which maybe is worthwhile doing. Yeah, still have time. So for the rest of the talks, I'll explain the example Spec F again in detail. I'll talk about the Birch-Swinnerton-Dyer case and compatibility with the functional equation. So this will be my remaining topics, and the motivic filtration also maybe. Okay, so let's go back to Spec F. So how does this picture look like? Again, the zeta function is just Dedekind zeta. I told you already in the first two talks that motivic homology is almost the same as K-theory. The difference is only two primary parts. So for example, the K3 of Z is not quite the same as motivic homology. We know the vanishing conjecture, which amounts to this classical statements. So I mean, I haven't told you what these complexes are for negative n, but this formula you just verify by looking at the gamma factors, and it really reduces to our vanishing order conjecture that was here. It's really that. I mean, okay. So now I want to rewrite our statement so that it looks like a class number formula, which is the least illuminating way to state all these conjectures. So you have the Weyer-Akelov picture, you have the fundamental line picture, and you have a third way of stating this conjecture so that it just looks like a class number formula, which is the least useful, I think. But you can do it. So let's see what we get. So the key ingredient is the Beilinson regulator, which replaces the unit regulator for n equals 1. So this would just be the units. And in higher degrees, we have the K groups, 2n minus 1, tensored with R. The Deligne homology is very easy. It's just a bunch of copies of R where if the place is complex, then it's just this 2 pi I n minus 1 R. If the place is real, then if n is even, then because you take Galois invariance, it's 0 here. So you get the right ranks from this. And it's known in this case that the Beilinson regulator induces isomorphisms on the real vector spaces. So that's a finitely generated group, and that's the corresponding real vector space, which for n equals 1 is just the unit regulator. Except for n equals 1, there's a slight difference. You have to take the sum 0 subspace. Because the units satisfy the product formula, so you land in the sum 0 subspace. Now, in general, there is an obvious analog of the class number, which is just the H2, which basically is the even K groups up to powers of 2. So that's the higher analog of a class number, clearly. And then the higher analog of roots of unity is just the torsion in this finitely generated group, which, again, you can compute completely explicitly in terms of the Galois cohomology of the roots of unity. So that's the higher Wn. And then you have a higher regulator, which is just the volume of the co-kernel of this regulator map. So that's finitely generated going to a real vector space. The volume of the co-kernel you take with respect to another Z structure here, and that's this Z structure. So that's why we have to put this factor 2 pi I to the n minus 1 to form this regulator term. We have to put the right power of 2 pi in there. For n equals 1, you don't see it. It's just Z, which is the classical regulator. You take the Z structure coming from just this Z lattice here in the class number formula. Okay, and so once you introduce all these terms, you get that our conjecture looks like a class number formula. So for negative integers, it's just that expression. If you remember the class number formula at n equals 0, it also looks like HR over W, but now you have these higher analogs. And at positive integers, where you have an actual value rather than a leading coefficient, our conjecture says that. And so it's a certain power of 2, a certain power of 2 pi, class number regulator, roots of unity. And then the interesting bit is this additive stuff. So first of all, we have this correction factor, right, which before we knew about TC plus, you had to put in this by hand, right? It's just the factor that makes the formula correct. And this comes out from derived de Rham cohomology, which I'll explain in a minute. So at least derived de Rham cohomology is already better than naive de Rham cohomology, which would only give you this the square root of the discriminant. But you get the right power of the discriminant as well. And now I'm just restating the theorem I had before. So these formulas are true for any n if f is abelian. It's just the restatement of our conjecture in the style of the class number formula. Okay, so where does this additive stuff come from? So this has to do with cyclic homology, which people sometimes call additive K theory. So we've seen this a number of times now in this workshop. So Hochschild homology is just, you may define like this. Cyclic homology is a derived S1 co-invariance on Hochschild homology. And then you have a motivic filtration, which was defined by Antjo. I mean, it was mentioned in Ben's talk at this conference. The spectral sequence actually is already appearing in an earlier paper from the 1990s by Machadas. So he looked at the corresponding spectral sequence for cyclic homology already. So the graded pieces of the motivic filtration on HC is just this truncated derived de Rham cohomology that I had on the board before. So this is sort of analogous to the motivic filtration on K theory, which gives you motivic homology, twisted and shifted. So that's why this is called additive K theory sometimes. I mean, it has an analogous structure, and it's somehow related to the tangent space of K theory, but that's kind of very mysterious. I mean, yeah. Well, the H0 is really in the weight 1 part. So if n is 1, you should get the H0. I mean, the H0 is just the additive group. It's just, let's say X is OF. Um, the cyclic H0 is the additive group, but it's the tangent space of the weight 1 motivic homology. Yeah, so it's because of the definition, yeah. But yeah. Yeah. Okay. Ah. Yeah. Ah. Ah. Yeah. Yeah. But that's just a question of this notation. The definition should be correct. It's a motivic weight n-graded piece on TC plus. Yeah. Okay. So again, this discussion is before TC plus came into the picture. So we were working with this derived de Rham cohomology, and this goes back to Ilyus's thesis. So you can use the techniques Illusi has in his thesis to compute this thing in a simple case like Spec OF. So you find that this derived de Rham cohomology is just a two-term complex, which in degree 0 has OF, and then it has some differential to a finite group of cardinality, this power of the discriminant. Yeah, so there's a natural filtration, and from that filtration you find that the group in degree 1 is just some finite abelian group of this cardinality. And the differential is, well, it is the Kähler differential. I mean, the Kähler, the D in the Kähler complex if n is 2, but not for higher n. And then the cyclic homology or the additive K theory in this very simple case just has two pieces. It's the kernel of this map and the co-kernel of this map. And the kernel is a lattice, is a sublattice of OF, and the co-kernel is some finite group, by what I'm saying here, right? I mean, that's clear. But we don't know what the differential is in general, so we cannot actually compute the cardinality of this co-kernel and this sublattice explicitly. But we can compute the Euler characteristics somehow. So in other words, the additive regulator of this sublattice times the additive class number, which is just the cardinality of this finite group. If you put them together, you get exactly this term in the zeta value formula. Even though you don't necessarily know the individual groups. This is also a little bit like in Achim's talk. You have the quotient you can compute, but not the individual groups. Yeah. Well, I mean, what do I mean by regulator? I have some sublattice of OF, and I take the regulator map, which sends F to F tensor C, which in turn is a natural direct product of all complex embeddings. And then for each embedding, I take the obvious basis. In other words, I relate a basis of OF with the indecomposable idempotence in F tensor C. And then the regulator between those two bases is my additive regulator. And if I take OF itself, it would just be this, right? But then I have some sublattice, and the regulator times the class number is this. Yeah. Okay. So how can we improve on this? And so this was also discovered experimentally by Baptiste. He looked at this paper of Madsen and Lindenstrauss computing THH of OF. And there you have this mysterious J in here, which if F is Q goes back to Böckstedt, I think. And this theorem of Madsen and Lindenstrauss actually can be proved in different ways. One proof was in Ben's talk on Tuesday, using this Gauss-Manin connection idea and relative THH gives another proof of this. So this is now a well-established theorem in THH theory, and but it goes back to these authors in 2000. And then, if you take THH and you try to compute TC plus from it by the obvious spectral sequence, namely this one, again, you cannot analyze the differentials, but you can tell what comes out eventually, that this Tc plus 2n minus 3 is a finite group, and Tc plus 2n minus 1 is a sublattice. And again, if you take the regulator of this sublattice times the cardinality of the finite group, you get the entire factor here, including this correction factor. So the factorial comes from all these j's here if you run them through the spectral sequence, converging to Tc plus. And so now we can reformulate our class number formula for higher n in this form where we have no correction factor anymore. So this is now clearly an additive class number, cardinality of this, and some additive regulator. Okay. And so the idea is now something similar should be true for higher dimensional schemes, not just OF, but any X. And so we need a motivic filtration on Tc plus of X. And again, in this basic case, it's just a double-speed Postnikov filtration. And in general, it was defined by Morin, and I think also by Lori independently. It's just globalizing the Bud-Morrow-Scholze filtration. And I will say a little bit more about that in my last talk. But what you can compute is, if you do that, so you combine the filtration from Ben's talk on HC with the Bud-Morrow-Scholze filtration, and you get a motivic filtration on Tc plus. And what you show is that the difference between the graded pieces, which for HC is derived Ra mod fil n, and for Tc plus, Lars just told me I shouldn't call this, but okay, it's just I define this to be the graded piece. And again, you run through the definitions, and you can compute the difference between these two theories. It's just this correction factor we had on the board before. It's this particular combination of factorials. But that's a non-trivial computation. I mean, you have to introduce another filtration that was defined by Morin. So you get a bifiltered object, and then on those graded pieces for the bifiltered object, you can see the factorials coming out. Okay, so maybe for today I'll stop here. In my last talk, I will say a little bit more about the Birch-Sweater-Dyer case and compatibility with the functional equation, where really this precise shape of this factor will play a role. You cannot allow any indeterminacy if you want to make an integral conjecture. And I will also say a little bit more about how this motivic filtration is actually defined, even though we've seen most ingredients already in this workshop. So for today, I think I'll just stop at this point. Yeah.
So can you localize, say, your conjecture that scheme phi is equal to C, so do some conjecture for that scheme that we see?
Yeah. I mean, I could write something. Am I allowed to use this board for the recording? Or I don't know. It would reduce to something like the following. So maybe I can erase this. Okay. Is it okay? Okay. So since I finished a little earlier, maybe I can say this. to X mod P. So let's call this some relative TC with respect to P or something. And I have the same for TC plus, and so the TC plus of this thing, if I rationalize it, so this tensor, I don't know, let's see, Q, it is just, as I said before, it is just, it is HC. I should take motivic graded pieces everywhere, so I leave the complete group. So this is HC, X over QP. And I think, but this is, I haven't checked, that TC is also rationally this TC. I mean this relative TC. Tensor QP. So this should follow from this paper on the valence and fiber square by Antio and others, I think. So rationally, this relative TC is also just HC. And then what I would need is that the integral lattices coincide. So not as actual complexes that TC plus is isomorphic to TC, but just on the level of determinants. So the determinant ZP of this TC plus is, well, it's actually equal. I mean, now I can really write equal because I already have isomorphisms on the rational spaces. So as sublattices of this same rational space, they're actually equal. So so that's the kind of statement one would need to prove that C infinity is really equal to C. So somehow. Yeah, so I mean, don't pin me down on this. There's experts that should be able to confirm or disprove this. So this should follow from this valence and fiber square. And I want everything on the motivic n-grade. So this is not a perfect complex. I want to put everything motivic n-graded piece. So yeah. No. Yeah. No, they're perfectly well defined because I define them by motivic homology, not by K theory. And I think for the even ones, they actually, okay, no, I'm not sure. I use motivic homology and there's no ambiguity then. Yeah. Only if you want to write them in terms of K groups, but you can use higher Chow groups, motivic homology, and then these would be the right groups.